Good. So in this class, I want to tell you about kmaps, which is essentially a manual simplification technique, sort of similar to the Boolean logic that we've encountered before. But we'll see that there's certain applications where kmaps are going to be much more convenient than sort of standard Boolean minimization. Okay, but before I explain how to use kmaps, let me just introduce a few definitions. Or just remind you that if you want to learn more about kmaps, these are the sections in the book that you might want to read. Then another term that we've already encountered is the sum of products form, which is essentially a function that's written as an OR operation of several AND gates and inversions only over input, so something of the form given here. Another term, another definition that's going to be useful is the terms onsets and offsets. So this truth table here specifies a function h, and the onset is the set of input patterns where the function is true. So specifically, the onset here, it's this row, this row, this row, this row, and the corresponding terms are not x, not y, z. The next one is not x, y, z. Then we have x, not y, not z. And x, not y, z. Okay? And then of course the offset is the set of input patterns where the function is false, so that's all the other four terms in this case. So that's onset and offset. Good, so now let's talk about simplification. Okay? So the key tool for simplification is the so-called uniting theorem, which kind of says that if you have something like a function of a and not b or b, this is really just a. Okay? So let's look at this first example here on the top left, where you have a function f, and you want to determine what f is. So you essentially have to look at all the terms belonging to the onset, so where the function is true, and you can write down the corresponding terms. That's going to be f. So f is equal to a and not b from here, or a and b. Now as you can see, b's value changes within the onset rows, and so b is essentially eliminated and a remains, because a's value don't change as indicated here within the onset rows. Okay, so that's the basic idea. Like if both the variable and its inverse occurs within the function and nothing else changes, then you can get rid of that variable. So just as a second example here, this function g, the onset is the first and the third row. So from here, the first row, we have not a, not b. And from here, we get a, not b. So you can immediately see that that a occurs, that a's value changes, but b's remains constant, so the expression is just not b. And so the essence of simplification, and this is obviously very, seems very obvious here, but the essence of simplification is that you have to find two element subsets of the onset where only one variable changes its value. And this single variable can be eliminated. Okay? And actually, if you look at these two examples, I would say that just visually, the top one was a little simpler than the bottom one, because in the top one, the onset values sort of occurred next to one another, and it was kind of easy to see that a remains constant but b changes. While that wasn't quite true in the second row, where the onsets were sort of spread out across the truth table. Okay? Good. So kmaps are really just a tool that help you sort of visualize. It's an alternative method of representing the truth table, and it helps you visualize adjacencies in up to 4 dimensions. So it makes it easy to see how which variables change and which ones stay constant within a certain within an onset. Okay, and kmaps, are useful with truth tables up to the size of 4 with up to 4 inputs, and beyond that it's essentially not possible to do this visually, but it actually is kind of an elegant method for these smaller logic functions. Okay, so before I'm telling you how I'm going to use kmaps for simplification, let me just define how they are, what they are, how they're written. And let's do this for 2 variable, 3 variable, and 4 variable kmaps. Okay? So here in the 2 variable kmap, you have the 2 variables a, and a in the along the y-axis takes the values 0, so this is a equals 0, and here a equals 1. So the line here indicates that this is where a specific variable is true. Similarly, b here, b equals 0, b equals 1 in the bottom row. So the corresponding terms are not a, not b, a, not b, not a, b, and a, b. Okay? Just essentially this a different way of representing the truth table. For 3 variable kmaps, you have the pair AB up here, and this pair takes the values 0, 0, 0, 1, and then 1, 1, and 1, 0. Okay, so again, here A is true, here C is true, here B is true, and then of course this is C is 0 or 1. Okay, and you notice that there's already something a bit different from what you would intuitively do, which is that the ordering is not 0, 0, 0, 1, 1, 0, 1, 1, but it's ordered 0, 1, 1, 1, 1, 0. And the point of this ordering is that from each column to the next, only one variable changes its value, right? So here you're going from A equals false to going to A equals true, and then in this next transition you go from B equals true to B equals false. Okay, and the fact that you have only one thing change, going from any one box to another, that's kind of what helps you bring. That's what helps you visualize these adjacencies. Okay. So of course, just for completeness, so in here you would have then the terms not A, not B, not C. Here you have not A, B, not C. Here you have A, A, B, not C. And up here, over here, you have A, not B, not C. And then down here, you have the same thing with just C instead of not C. Okay, great. Finally, 4 variable kmaps. Same idea. So here, A is true in these columns. B is true, D, and C. So the values of A, B are 0, 0, 0, 1, 1, 1, 1, 0. Similarly for C, D, 0, 0, 0, 1, 1, 1, 1, 0. And then of course just filling out the corners. This is where all 4 variables are false. In this corner, we have not A, not B, C, not D. Over here, we have A, not B, C, not D. And up here, we have not A, not, sorry, this is wrong. This is A, not B, not C, not D. Okay? Good. So this is just how you actually organize the kmap. Let's just do this as an exercise again. So here are specific function examples. And what you want to do, and maybe you could quickly do that before watching me do it, is just take these truth tables and fill the values into the right places in the kmap. Okay, so here, let me show you now how it's done. So again, as a reminder, right, so here is A is 0, 1, B is 0, 1. So obviously here you have 0, 0, so that's the top half of the truth table, and then you have 1, 0 here. Again, here I'm sort of going to do this pair by pair. I can just start copying these first two columns, so that's 0, 1, 1, 1. Now I have to be careful, 0, 0, 1, 0. So here, right, the ordering of the truth table is different from the ordering of the kmap, because again, here I have 0, 0, 0, 1, 1, 1, 1, 0. And then finally, the 4-variable kmap. Again, I'm going to do it essentially in column by column within the kmap. But now I have to be doubly careful, because when I'm copying these 4 values over here, I also have to flip the last 2 bits. So it's 0, 0, 1, 0. I'm going to take the next 4, 1, 0, 0, 1. And then, so in each case, flipping these 2 bits. I'll keep doing this, but again, I'm also flipping these whole stacks of values to get 1, 0, 0, 0, 1, 1, 1, 1. Okay, so if you have that, great, then you essentially know how to convert from a truth table to a kmap. Good. So now we come to the reason why we actually introduce kmaps in the first place, which is to use them for simplification. Okay. So what you're going to do is you're essentially gonna try to identify. You're gonna do what we've done a few slides ago, which is try to combine terms where a variable, the value of one variable changes, but another one stays constant. And the way you're going to do this is essentially by going to drawing circles around the onset. Okay, so let me show this. So in this particular example, I have 2 1s, and I'm going to circle them like this. And I'm going to look at this circle, and I'm going to say, well, it falls within the column where A is true, and it crosses this boundary from B equals being false to B equals true. And so this function is simply f is equal to A. Okay. Now let me do this slightly differently. And let me instead draw circles about each A individually. Okay. If I did this, then I would say, well, there's 2 circles. This one here is A, not B. And this one here is AB. So I can combine these. And that's, of course, A. So essentially what I've done by sort of making this blue circle as big as possible and covering as many 1s as I can, is I've essentially already done the minimization. So I can immediately read off the kmap, the minimized version of the function, without actually having to do the math as I've done for the red case. So before showing you a few other examples, let me first sort of define the rules of the game. Okay, so as I said, you want to circle all the ones. All ones need to be in a circle. Good. Bigger circles are better. Okay, as we've seen, I mean, the more you can expand the circle, effectively, the more the more minimal or minimize the function that you get, that you read off, will be. And then the final important rule is that circles have to have powers of 2. So that could be 1 by 1, 1 by 2, 2 by 1, 2 by 2 by 2, what else? 1 by 4, 4 by 1, 4 by 4, and probably I forgot a few. Okay, 2 by 4, 4 by 2, of course. Good. And the reason why that's the case is because essentially, this is again why it works in the first place, is because in every circle you're trying to essentially cover a variable that takes both values. So for example, in this case here, the blue circle covers the two terms where a is constant but b changes. Okay, and so obviously any circle needs to kind of have at least one variable that takes both values, except in the 1 by 1 case. So if you had a 1 by 3 circle, that's sort of hard to interpret, and it's essentially not useful for this kind of minimization. Okay, so let's do another example. So over here, again, there's essentially just one circle. And in this case, well, you can see that it falls within the row where b is 0, and it crosses the boundary from a equals 0 to 1, so this essentially is just not b. Okay, so let's move on to the slightly more complicated kmaps down here. So here I can draw essentially 3 circles. Okay, so this circle here is A, B, so it's within A being true and B being true, but it crosses the C boundary. This here is A, C in, and this here is B, C in. Okay, so the function is AB or AC or BC. So what I've done here is that I've used this one term corresponding to, what is that, A, B, C, several times, which of course is sort of a legal operation because, you know, for example, ABC or ABC is still just ABC. Okay, so I can actually reuse that, which is often convenient because it allows me essentially to make bigger circles than if I just used it a single time. Good. Now finally here, it's kind of a simple example. It's just a different shape circle, and of course this is a bigger circle, so it's A is true, and but it both crosses the C not C and the B not B boundary, so this is just A. So again, the larger the circle, the more compact the final function. Okay, so let's do one other example, and I think at this point I recommend that you try to do this yourself again. So you've seen the basic idea. So instead of just watching me do it, pause the video, think about what the circles should be, what their values are, and then compare to my solutions. Okay, so in this particular case, I'm going to draw one circle here. I'm going to draw a circle here, which we're actually not going to use in the end. And I'm going to draw a circle here. So this is kind of a new thing. You may or may not have figured that out for yourself, which is that these kmaps essentially wrap around. So the way to think of this is more like a cylinder. Since you're going here from the values of a, b being 0, 0 to 0, 1, 1, 1, 1, 0, again, it's just one bit change to go from 1, 0 to 0, 0. So it's kind of, you have adjacency from this to this edge, and you can again expand. Instead of just making a circle about this single one here, you can expand the circle and have it cover both of these ones, which will give you a more minimal function. So the circle here is necessary, the bottom circle, to cover this one, so there's no other circle that does that. The circle here is necessary to cover this one, and these two circles together cover everything. So even though you can make this circle and it has size 2, you're not actually, it doesn't actually give you anything, right? So in this particular case, the function is essentially just, what is this? Top one is not BC, and the bottom one here is AC. If you want to get f bar, you can essentially replace ones with zeros and vice versa. So this is the function f bar essentially. Here, that's the corresponding kmap, where it just flipped ones and zeros here. And now I'm just going to circle the ones again. And in this particular case, if I get these two circles, that covers all the ones. Like this bottom one is necessary because of this one. This top circle is the only large circle covering this one. And so we don't need this central circle because all of the ones are already covered. And of course the function f bar here is simply b not c, or what is that? Not a c. Okay, and then you could convince yourself that this actually is the correct inverse of f.